Okay, so welcome back to week three's problem solving session. So today, what we'll do is we will look into a different class of problems, which I feel is a one step ahead of the problems that we solved in the previous week, which was unidirectional rectilinear flows. Of course, it was steady, but in this week, what we will see is we will look into something which is known as an axisymmetric flows, which is of course obviously unidirectional and steady. Maybe I should add the word unidirectional here. So it's steady plus unidirectional. But instead of it being rectilinear flows, we'll look into something which is known as an axisymmetric flows. Okay. So I believe you have looked or gone through the lecture series in this week, where you are accustomed to or you were exposed to something which is known as an Hagen-Poiseuille flow, which was like so there was a so you can maybe think it of like there is a pipe, okay, and you are some kind of applying a pressure gradient between stations, let's say 1 and 2, uh, which were at pressure P1 and P2. And let's say if P1 is kind of like greater than P2, you can interpret this like having a constant pressure gradient, which is of the form dP by dz, where your z is basically in this direction along the axis of symmetry of the pipe. And because of this pressure gradient, the fluid basically moved maybe in this direction, which of course it will if your P1 is greater than P2, you'll have a pressure gradient along the z direction, meaning the positive z direction, because your dP, oops, I think I made a mistake. So if your P1 is greater than P2, this means that, if you calculate dP, it is going to be, so your dP is going to be some minus times of G, simply because your P2 becomes less than P1. So the principle is because of the fact that you are having a constant pressure gradient between two different stations, the fluid actually will move depending on the magnitude of P1 and P2. It can either move along the plus z direction or the minus z direction. Now, what you learned is you considered certain assumptions. For instance, the assumptions that we saw in the previous week, like the steady, unidirectional, and fully developed. Using all those assumptions, what you did is you basically derived the velocity profile, which is uz. Uh, Now that you need to understand that we are now transitioning from the Cartesian space to the cylindrical space, so we'll be dealing with cylindrical coordinate systems in these kind of flows, which typically is denoted as r, theta, and z. So the corresponding velocity field, which was u, v, and w in the Cartesian space, now we will denote it as like the ur, u theta, and uz. Okay. So what you saw is that in these uh, flows, which we call it as the circular parabolic flow, or sometimes it is also called as the Hagen-Poiseuille flow. That's the more common name that fluid dynamics use. But you can also call it as the circular parabolic flow. What you saw is that you had a non-zero uz, which is just a function of r, and you saw that this is some kind of a parabolic profile which has a functional. So if this radius, the pipe radius is r, you saw that this is equal to something like 1 minus 1 by 4 mu dp dz times r square minus r square. I think this is how the velocity profile look like in case of a circular parabolic flow. Okay, so certain things that you need to understand when you switch from Cartesian space to the axisymmetric cases, that first of all, what exactly is the meaning of this word axisymmetry? Okay, this is something that you need to understand, and the answer to this is the fact that the definition of axisymmetry actually differs from coordinate systems to coordinate systems. First of all, you cannot define axisymmetry in Cartesian space, typically because so Cartesian geometry is a plane geometry basically. So there is no definition of axisymmetry. So there is no, I mean the word axisymmetry doesn't what to say, doesn't applies to Cartesian spaces basically. But in case of curvilinear coordinates, so these kind of coordinates like cylindrical coordinate, or sometimes we also encounter a coordinate system which we will see later on in this course, which is known as the spherical coordinate system. And this is generally denoted as maybe RS, where RS is the spherical radius, theta and phi, where this RS is known as the spherical radius, theta is known as the polar angle, and phi is known as the azimuthal angle. So these kind of coordinate systems, like the cylindrical coordinate system or the spherical coordinate system, these are actually known as curvilinear coordinates. Okay. So in curvilinear coordinates, you can always define something which is known as the axis of symmetry. For instance, let's focus on the cylindrical coordinate, because that is where we are actually going to write our equations. So in cylindrical coordinate, where you can infer that maybe if I have my z-axis in this, let's say I have my z-axis in this direction, and I can, for instance, I can look into the motion of a fluid flowing through a pipe, as I have drawn in the above figure. So typically this is how it will look like. So you can infer that the axis of the pipe, okay, the axis of the pipe is coinciding with the z-axis, as you can see here. Okay. And if I draw the projection of the cross-sectional area, the cross-sectional area will essentially come in the r theta plane basically here. Okay. So if I draw the projection, as I was saying, the projection, I hope you guys can realize, is going to be a circle, because it's a cylinder basically. So, and in this circle, you can then define something known as, so basically, so this is basically the projection that I'm drawing, and these are my x and y axes. Okay. And then I can define, r, which is nothing but, the cylindrical radius, and then theta, you can consider it in this direction basically. So I hope you realize that the z-axis is essentially so basically the z-axis is perpendicular to the plane containing x and y, basically in this direction. I hope you can realize that. Okay. So the meaning of axisymmetry in case of cylindrical coordinate is that if you move around the z-axis, okay, that is in the direction of theta here, because basically what you are doing is, when you're moving along theta, you're basically doing something like this. So you're traveling around the z-axis, something like this. Okay. So the meaning of axisymmetry in cylindrical coordinate is that if you move around the z-axis, that is in this form, okay, your variables are invariant, which means in mathematical terms, if let's say your v is a variable, okay, so v is not a function of theta. Okay. This is what axisymmetry means in cylindrical coordinate. Okay. And this is something that you need to understand when you are dealing with curvilinear coordinates, because it actually simplifies our analysis when we invoke the assumptions of axisymmetries. And this typically means what essentially is axisymmetric. Okay. In other words, in realistic terms, for instance, if I consider a flow that is flowing, let's say in this direction, and I say that the flow is axisymmetric, which this means that if we move around the z-axis, I hope you can understand, or maybe through this figure. So if we move around the z-axis, my flow field is going to be is not going to change. Or in other words, if we go by the coordinates, then I can say that my flow field, or whatever variables I'm looking at, it can be flow field, it can be scalars like temperature, density, whatever it is, they are not a function of theta. This is what is the meaning of axisymmetries. So this is typically what is meant by axisymmetric condition for cylindrical coordinates. Okay, so when you derive the velocity profile for the Hagen-Poiseuille flow or the circular parabolic flow, what you essentially did is that you invoke the assumption of axisymmetry, meaning that your uz, which is the z, the z direction velocity, this uz is not, so this uz is essentially not a function of theta. This is an important assumption that we didn't use actually in Cartesian coordinate, but it needs to be taken care of when we are actually looking for solving problems in curvilinear coordinates or in cylindrical coordinates. And that's the reason why this is also called as an axisymmetric flows. I mean, this is where the name comes, the axisymmetric flows. Okay, it just means that whatever variable you are actually trying to solve for, they are not going to be a function of the coordinate which you get when you move around the axis of symmetry, which becomes the z axis in this particular scenario. Okay, this is actually what axisymmetry means. Okay, so this is something that I wanted to clarify before going ahead. And the second thing that we have looked is something known as a flow between two cylinders, or flow between rotating cylinders. And we are actually going to solve a problem after this. As you will see, where we will invoke this so we'll invoke the concept of Hagen-Poiseuille flow and flow that is generated by two rotating cylinders. So we'll kind of look into a combined effect of these two flows and solve the problem. The simpler ones, as I said, I mean the individual cases we have already looked in the lecture series. Okay, so you have also looked, as I said, you have also looked into something which is known as a flow between two concentric cylinders. This is typically known as a Taylor-Couette flow, where you saw that there was, again, I'll draw a cylinder here, maybe. So it's like, maybe I'll draw like dotted lines. So maybe you had a cylinder which is of this form, okay, and maybe something like this, okay, and you can also have an inner cylinder which maybe is of this form. And then what you are doing is, again, we'll have the axis of symmetry, okay, which again is our z axis in this scenario. This is typically my axis of symmetry. So what you do is, now instead of adding a pressure gradient along the z axis by maintaining two different pressures at two different stations, what you are doing is you actually kind of actuate the fluid. You kind of rotate the fluid by imparting rotational velocities to this cylinder. So what you typically do is you say that maybe the outer cylinder is kind of rotating. You basically say that maybe this cylinder is kind of rotating around the z-axis by some, let's say, omega 1, and the inner cylinder is also rotating about the z-axis by some, let's say, angular velocity omega 2, where omega 1 and omega 2 are angular velocities of the inner and outer cylinder respectively. So I hope you can realize that what you are doing is, so typically if I now draw the cross-sectional view, I hope you can understand that we have, so the cross-sectional view is going to be two concentric circles. Maybe this is going to be this. This is going to be this, and then, okay, something like this, okay. Okay, so this is what the cross-sectional view will look like, and then you are saying that the cylinders are actually rotating. The cylinders are actually rotating with some angular velocity omega 1, and the inner cylinder is also rotating with some angular velocity omega 2. Okay, which then means that the fluid inside the cylinder, which is present, I hope you can realize that this fluid, which is inside the annulus of these two cylinders, and this is something that you have derived, this will also rotate. Okay, this will also rotate with some with some velocity, and the objective was basically to find out the velocity field. And you saw that this time the velocity field will have a non-zero u theta component of velocity field, and again invoking the assumption that the flow is fully developed, it is axisymmetric. As we have discussed, you saw that your u theta is just a function of r only. Okay, and this is obvious, right? Because when you move from this space to this space, you actually will see a change in your velocity profile in the u theta component because of the two different boundary conditions that are imposed on the surface of the two cylinders. Okay, but you have, so your fully developed condition in this scenario will say that your uz component of velocity is 0. Okay, uz equal to 0, and using the fact that, and we will see this, the detailed explanation of this very shortly, that if you impose something which is known as a no penetration boundary condition on the surfaces of the two cylinders, you can argue that your UR is also going to be equal to 0. Which means that this is also a special class of unidirectional flows, because we only have a non-zero u theta component of velocity, which is just a function of r. And I hope you can realize that again we will encounter an ODE which we actually require to solve, for which we have two boundary conditions, which are nothing but the rotation of the inner and the outer cylinder. Okay, But so these kind of flows are known as Taylor-Coate flows, and this is something that you have, and deriving the velocity profile in this scenario is something that you have done in the last in the lecture series. Okay, I mean you have witnessed in the lecture series of this week. Okay, so keeping this motivation in mind, as a you know as an what to say, as a discussion problem, what we'll do is we'll try to now solve a problem which is kind of a superimpose, which is kind of a linear superposition of this problem and this problem basically. So we'll now look into a problem where the fluid will also move axially, because there is an axial pressure gradient that is being applied along the length of the pipe, and also it is basically confined along two rotating cylinders, which means that the fluid will also possess a u theta component of velocity. Okay, and again we will then show that the two solutions are basically going to be so whatever the solution that we will derive, they are actually going to be not dependent on each other, typically because all the assumptions that will invoke will actually result in this scenario. But yeah, we will see that essentially we'll look into, I mean, we will see that the velocity profile will contain now two components of velocity, one for the axial motion of the fluid, which will be uj of r, I hope you understand, and one for the rotation of the pipe, which will be u theta as a function of r. Okay, so this problem that I was telling you, I call this as the fluid dynamics of an extrusion process, and you can see this on your screen. So typically, before going into the fluid dynamics part, I want to little bit shed light on what is known as an extrusion process. So this is a term that people use in material sciences typically. Also in mechanical engineering, you might have heard this in your BTech, I mean in your bachelor's when you learn manufacturing or material science. So yeah, typically it is used basically in material sciences and manufacturing processes, where this term extrusion means is you kind of first insert a material. This material is, so generally this material is a molten material, which is generally, whose phase is liquid, and you insert them in between some things which is called as a die. Okay, so these black objects, as you can see, which is here, for in this case this is in the shape of a cylinder, they are typically known as dies. Okay, and then what you do is after inserting them, so the reason why you want to insert the molten material in between these die is that you want the molten material to actually get a particular shape. Okay, that's, so for instance, if you want to get a ring, basically what you do is you prepare two dies which are concentric cylinders and then insert the material in between the two die. So then so basically if you do that, and if you give some thickness, I mean if you give some length of this die, I hope you can realize that when the molten material solidifies, you will basically get an annulus with a prescribed length, and that's the shape that you are actually you are trying to manufacture. So the idea is that you put the molten material in between these two dies, and then what you do is, after inserting the molten material, you also need to take out the molten material, right? Then only you can reuse the die for creating some other, or creating the second batch of materials. So what then you do is you apply a pressure. So basically what it is done in the industry is that so a pressure gradient is applied such that the molten material basically comes out, and then this process can be repeated for the next cycle. Okay, so it's very simple. So you first put the molten material in between the die, which is the case of two cylinders in this scenario. The shape of the die, as I said, depends on the end product that you are going to manufacture. But once you put the molten material in between the die, then after some time you also need to take out the molten material, for which you apply a pressure gradient, and this pressure gradient actually results in the motion of the fluid in the axial direction, as we will see here, which takes out the fluid, and then the fluid solidifies and gets the desired shape that we are trying to manufacture. Okay, so this is the overview. I may not be very technically correct about the terms that I have used here regarding the manufacturing process of extrusion, but this is the broad idea, or a layman's term of understanding what an extrusion process is. Okay, what we are interested in is actually trying to understand the fluid dynamics that is behind this extrusion process. So for that, what I have done is, we need a die, of course, and the choice of the die that I have made here is that I have considered two concentric cylinders, as you can see. Okay, so one of the cylinder, I call it as maybe the outer cylinder. This have a radius of b, and this is rotating with some angular velocity omega 2, and the inner cylinder is rotating with some angular velocity omega 1. And then we have the molten material or the fluid, which is between the annulus, or which is inside the annulus of these two cylinders. And you can see that by this blue color that the fluid is inside this. And of course these cylinders are rotating. Typically these cylinders rotate because you don't want the molten material to stick inside or to remain or get accumulated in a particular space. So you provide a constant rotational velocity to these cylinders. That's typically the standard process of how these kind of extrusion takes place. Now what you're doing is, as I said, you also need to take out the molten material, and just by giving a mere rotation to the cylinder will not lead to the fact that the molten material will come outside the die. Okay, so for that what you need to do is you also need to have an axial motion of the fluid. And because of that, as I said, what typically is done is people apply an axial pressure gradient, which for simplicity you can consider it to be uniform. But you need to understand that the magnitude of this pressure gradient is very, very high, because you need to take this hot molten material outside this die, right? It is typically in the order of megapascals. That's the typical. I was checking the internet today, and that's the typical pressure that people apply when they want to take out the molten material from the die, basically. Okay. So, but again, since we are only interested in the fluid dynamics as far as the scope of this course is concerned, we are not going to, we're not going into the details of the precise magnitude of the pressure gradients and the dimensions of the die and things like that. Okay. But as I said, this is just a prototypical system, which you can analyze in order to get an idea of how the fluid dynamics in an extrusion process actually takes place. Okay. So that's what you do basically in order to move the fluid out of the die, as I was saying. Okay, so as you can understand, there are now two motions: one, the rotation of the cylinders, as you can see, and second, the motion of the fluid, which second, you also need to move the fluid axially outward, because of which you apply pressure gradient in the z direction. Okay, now given this scenario, what the problem actually wants us to solve for is to get the velocity field. That's typically what we need to do, just as we had been doing in the previous examples. Okay, so that's the idea. So maybe I'll stop here for a couple of minutes such that you can understand the problem, and then we will look into the step-by-step solution of this problem. Okay, so I believe you have understood the problem. So let's get started then. Let's try to solve for the velocity profile. So couple of things that you need to understand, that we will use, as you can see from the figure, we'll use a cylindrical coordinate system. So we will, so that's, I'll write it down. So we shall write the solutions using a cylindrical coordinate system, which is r, theta, and z. Okay, where r, as we all know, is known as the cylindrical radius. Theta is the angle, basically is the polar angle, as I said. This we have seen in the examples that I have showed you just some time before. And z is basically in the direction which is aligned in the direction of the axis of symmetry of the object. Okay. All right. So before actually looking into the solutions, let's first try to understand the boundary conditions and how many velocity profile, non-zero velocity profiles, or I should say how many non-zero components of the velocity field will be there in this scenario. Okay. Now, first of all, you need to understand that if I want to write my velocity field here, which of course is a vector, I can then write it as in cylindrical coordinate, I can write it as v equal to ur er hat plus Okay, maybe I'll write it as V equal to UR, and at max, this velocity field can be a function of R, it can be a function of theta, and it can be a function of Z times ER hat, where these ERs are the unit vectors. We have been using this repeatedly. So the next component would be U theta times R theta Z. So I hope you understand that this implies that at max, your velocity fields will be a function of R theta and Z. This is the maximum, I mean, this is up to which it can actually, I mean, this is the maximum, probable variables on which, your velocity field can actually depend on. This would be E theta hat plus uz as a function of r, theta and z times ez hat. Okay, where I hope you can understand that we are now writing the velocity field in the cylindrical coordinate system, and these are now the independent variables on which your velocity field can at max depend on. Okay, all right, and so this is the velocity field. Let's name it as equation 1. Okay, and what we now need to understand that we are required to evaluate this v. That's typically is the objective that we need to evaluate, which means that we just need to evaluate what will be ur, u theta and uz, because if ur, u theta and uz are known, just multiply them with the unit vectors will give you the entire velocity field of the problem. Okay, so that's number 1. Number 2 is that let's try to understand the boundary conditions in this problem. So the boundary conditions are, okay, so let's see the boundary conditions. So first of all, I know that so if you want to look at the boundary conditions, you must look at what basically is happening at the cylinder surfaces, right? Because this is where the fluid is basically being enclosed. Okay, so you can see that if you just use the simple no slip boundary condition, you should say that whatever the fluid that is in contact with the cylinder surfaces, for instance like the red line that I am drawing, this should also move with a velocity omega 2 times v, to be precise. Okay, that is typically because of the no slip boundary conditions. So this means that I can say that my V at R equal to B, which is at the outer cylinder, for all theta and for all z, this is going to be the velocity of the cylinder typically, and the velocity of the cylinder is going to be omega cross r. This is something that we all know, because if I have an object which is rotating with an angular velocity omega, okay, its corresponding translational velocity is r time. It's basically omega cross the cross product of omega with r. Basically r is basically the axis from which, so this is typically r. I hope you can realize that it's basically the distance from which you are actually looking into the rotation of this object. Okay, this is basically your r, which is b in this scenario, because we know that there is only a rotation of the cylinder at r equal to b and at r equal to a. Okay, but in general it is going to be omega cross r. Now we know that omega is in the direction of Ez, because we can simply use the right hand thumb rule and say that if my cylinder is rotating in this direction, then its direction is basically going to be along the z, because if my omega is here, then its direction is always going to be along the z axis, which means I can then call it as omega, maybe, so this is omega 2, so I'll call it as, let's say, omega 2, it's with its direction Ez cross b er, because I know that my r is basically equal to b times er at 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 the outer cylinder surface. Okay, I hope this is clear, which means it is just going to be omega 2 times v Ez cross er, and if you simply use the concept of cross product, Ez cross er is going to give you an E theta, because this is a cross product between Z and R. It is just same like if you do I cross J, this is going to be K. If you simply do K cross I, it is going to be equal to J. That's the cyclic rule that cross product follow. And in cylindrical coordinate, you can easily extend this generalization and then say that Ez cross Er is just going to give you an E theta. Okay, which means then my velocity field, okay, this is important and you need to understand, my velocity field at r equal to b for all theta and all z is having just one component, which is u theta. So this means I can then say that my u theta at r equal to b for all z and for all theta and z is going to be omega 2 times v. And I know that then my ur at r equal to b for all theta and z, and my uz and at r equal to b for all theta and z, this is just going to be equal to 0. That simply comes from this fact that your velocity field has just one component when you approach the surface of the cylinders. Okay, maybe I'll call this 2, the second boundary condition. Similarly, you can then say, if you apply the same logic for the inner cylinder, everything else will just be the same. Then you can just infer that. I hope that you can just draw the same analogy here, and you can say that your u theta at r equal to a for all theta and z is going to be omega 1 times a. Okay, and you know that ur at r equal to a for all theta and z, this is going to be equal to uz at r equal to a for all theta and z, and this is equal to 0. Okay, which is my second boundary condition here. So I hope you realize that these are just the consequence of, so this 2 and 3, are just consequence of the no slip boundary condition. Okay, all right, I hope you are with me so far. All right, given these two boundary conditions now, I think we are all set to start the solution of this analysis. So let's then get started. So as I said, we'll be starting off with the assumptions. Okay. So because see, the objective is to evaluate these velocity fields, right? That's the ultimate objective. We just need to evaluate these velocity field ur, u theta, and uz. That's all that we need to know. For that, we have the boundary condition that we just now saw, that what can we impose on the surface of the cylinder, and after that, we just need to use these boundary conditions to get the constants as we had been doing to evaluate the velocity field. Okay. So before that, as I say, it's always a good practice to write down the assumptions. So let's start off by writing the assumptions. So the assumptions are as follows. So some are just trivial. For instance, we'll consider the flow to be steady. We will consider the flow to be fully developed. And we will say that the flow this time is axisymmetric. Okay, this is an important assumption which we hadn't been using when we are solving, one, state unidirectional rectilinear flows. Okay, and I hope you understand that this axisymmetric assumption actually makes sense. You know why? That is typically because if you look into this physical paradigm, you can see that there is nothing which, so there is no mechanism which can actually cause a variation of the velocities along the theta direction, because the problem is symmetric about the theta direction, right? Since the problem is symmetric, when you move along the theta direction, you expect that your variables are not going to be function of theta, simply because it is just symmetric along the theta direction, and that typically is something that you can physically interpret as the meaning of axisymmetry in this scenario. Okay, now had there been some mechanisms which would have said, or because of which there you can, if you basically break the symmetry along the theta direction, then you cannot use the assumption that your problem is axisymmetric in nature. But for this problem, there is nothing which stops us from using the fact that the, or asserting the fact that the problem is symmetric if we move around the z axis or in the theta direction typically. Okay, all right, and the other assumptions, these are trivial. For instance, we will consider no body force present, no body force, and we'll also consider the fact that the fluid is Newtonian. Okay, Newtonian fluid. meaning that we'll just typically use the Navier-Stokes equation to get the velocity profile. That's it. Okay, so these are the assumptions. I hope you understood. So the rest of the assumptions are something that we have already seen in the previous class. But I hope you understood the physical meaning of these axisymmetric assumptions that we have used here for curvilinear coordinates into solving this problem. Okay. All right. I hope this is clear. Then let's write the governing equation, because this is the next step that follows after writing the assumptions. So the governing equations. Okay. So first of all, the continuity. Okay. So if you apply, or if you write down, so continuity equation is what? So it is just divergence of the velocity field is zero for an incompressible fluid. So you can also write the fact that your fluid is incompressible. And throughout this course, unless mentioned otherwise, we will consider the fluid to be incompressible as well, such that this divergence form of the continuity equation holds good in so basically this holds good everywhere. Okay. We'll consider the fact that the fluid is incompressible or incompressible fluid. Okay. All right. So then we can use this form of the continuity equation, which is divergence of the velocity field is zero. And I know that my velocity field is going to be UR ER hat plus U theta E theta hat plus UZ EZ hat. Okay. And if you, so basically, if you look into the divergence operator, so the divergence operator in cylindrical coordinate look like, or the del operator typically in cylindrical coordinate look like 1 by R del R of R ER, okay, plus 1 by R del theta of E theta plus del Z of EZ, okay. So this is what the del operator, look like in cylindrical coordinate. And then if you take the dot product of this with this, you will just simply get 1 by R del R of R times UR plus 1 by R of del theta of U theta plus del Z of UZ equals to 0. Okay, so that's what the continuity equation look like in case of cylindrical coordinate system. See, the difference comes because now this factor changes. So it is 1 by R times del R of R. Basically, this is how it looked like. So this is how your gradients look like when you change from Cartesian to to curvilinear coordinates basically. And these non-zero things come basically because of something which is known as so there is something so I actually forgot the name, but you can actually derive that why this factor is 1 by R and not 1 by R square and things like this. So you can actually, so if you take take a course on curvilinear coordinates, you actually learn there how you derive these factors basically in curvilinear coordinate. But for this course, let's not go into the nuances of this, and then just use the form that we have at our disposal. Okay. But these factors, these 1 by R times, let's say R, these factors actually has got a name in when you basically study, you know, curvilinear coordinates in maybe as a maths course somewhere. All right, so that's what the continuity equation look like. Okay, so now let's first of all simplify this by invoking all the assumptions. For instance, if I use the fact that my flow is fully developed, which we all had been using, I can say that this term is 0 owing to the fact that my flow is fully developed. Okay, and then if I use the fact that my problem is axisymmetric in nature, then as I said, no, all the variables are not a function of theta, which means this term also goes to 0, and this is a consequence of the fact that my problem is axisymmetric in nature. Okay, axisymmetric assumption. which, as I said, means that none of your variables are going to be a function of theta basically, which then simplifies the continuity equation as 1 upon r del r of r times ur equals to 0, and then this gives us what, del r of r times ur to be equal to 0. And then if I just simplify this, I can then write it as, r times del u del r plus ur equals to 0. Okay, so this is something that we get when we invoke the assumptions in the continuity equation. Okay, maybe I'll name this equation as equation 4. All right, now this is something, I mean, this is something important that you that you need to understand. Okay, sorry. Okay, sorry for that. Okay, all right. So now, in order to get deeper insight into equation 4, we will use one of the boundary conditions. Okay, so I said that at r equal to a and r equal to b, if we look into these two equations, I said that my ur at r equal to b and my ur at r equal to a is 0, which means that when I reach, if I reach the surface, for instance, if I draw the cross-sectional view of the cylinders, I have my outer cylinder something like this, and then I have my inner cylinder, which is something like this. Okay. Okay. So what it says is that when I hit, when I go from the inner cylinder to the outer cylinder, I know that here my ur is equal to 0, and at the surface of the inner cylinder, my ur is equal to 0, typically from the no-slip boundary condition, which means that at the interface of the inner cylinder and the outer cylinder, my ur component of velocity field is 0, and typically this is nothing but the no penetration boundary condition. Okay, my fluid cannot so basically my fluid cannot have a radial velocity at the interface of the two cylinders, because these cylinders are non-porous in nature, or solid cylinders typically, which means that if my ur is 0 at this point and this point, and I don't have any actuating mechanisms which can generate a non-zero UR inside the fluid, this then means that at each and every point in the radial space, my UR is just going to be equal to 0. Okay, I repeat, from the no penetration boundary conditions, I know that my UR at the interface of the inner and the outer cylinder is 0, and I know that there is no mechanism inside the fluid which can generate a non-zero UR apart from these 2 points. This then says that at each and every point inside the fluid, my UR, that is the R component of the velocity field, this is going to be equal to 0 everywhere. Okay, so from the no penetration boundary condition, I can say that UR is equal to 0, or maybe I'll call it as UR, which at next can be a function of R, theta, and Z. This is equal to 0 everywhere. Okay, that's it. This is what the continuity equation actually gives us. Okay. Not only this, I can also say that okay, this is just an implication, because since ur is 0, I can also say that its derivative, so basically we'll also have all the derivatives which are just going to be equal to 0, simply because ur is equal to 0. Okay, so this means that the only non-zero components that we need to think of is like calculating u theta and uz. And not only this, I know that these are just going to be a function of r. Okay, so these are the only possible non-zero components of velocity. That is typically because I know that my problem is axisymmetric in nature, which means that my u theta is not going to be a function of theta. And from the assumption that the flow is fully developed, my variables, the non-zero variables u theta and uz, they are also not going to be a function of z, which then only means that u theta and uz, which are non-zero, we know that, but they are just going to be a function of r. Okay, that's the only possible scenario. So I'll write it down. So u theta and uz are functions of R only due to the fully developed and axisymmetric assumptions. Okay. Okay, all right. So that's it. Then what we need to do is we just now need to evaluate these two non-zero components of velocity, and we all know that these are so at this point these are just function of r only. Okay. All right. So I'll stop here maybe for a couple of minutes. If you have any questions, you can feel free to let me know. Okay, that's it. Then what we need to do is, I hope you can now guess the next step. We just need to write the Navier-Stokes equation in the theta and z direction to get the velocities in the theta and z direction, which is u theta and uz. Okay, so that's all we need to do. So we'll just write the Navier-Stokes equation in the theta direction. Okay, so this is little bit of a big equation, meaning that in cylindrical space we actually encounter certain additional terms. So I'll just write it down. Please bear with me till I write down the entire equation. Okay, so it is going to be rho times, that's the inertia term, del u theta by del t plus ur times del u theta by del r plus u theta by r del u theta by del theta plus ur. Okay, then I have plus uz del u theta by del z. Okay, that's the inertia term. And then we have the pressure gradient, which is 1 upon r times del p by del theta. Okay, then we have mu 1 by r del r of r times del u theta by del r plus 1 upon r square del square u theta by del theta square. Okay, plus del square u theta by del z square plus I have 2 by r squared del ur by del theta minus u theta by r squared. Okay, so that's it. That's the Navier-Stokes equation. That's the full Navier-Stokes equation written in the theta direction in cylindrical coordinate space. But even though it looks like a nasty equation, we will invoke the assumption and we will see that we'll simply, this equation gets reduced to a simple ODE, as we'll see very shortly. ODE meaning the ordinary differential equation. Okay, so first of all, let's use the fact that my problem is steady, which means that this term just goes to 0. I know that my UR is 0, so let's first cancel this. Okay, I know that UR is equal to 0, and I also know that my problem is axisymmetric, which means that del theta is just going to be equal to 0. I know that my problem is fully developed, which means that there aren't going to be any variables which are also dependent on z. Again, axisymmetric, del p del theta equal to 0. Okay, then axisymmetric again, so second derivative with respect to theta is 0, second derivative with respect to z is 0, which means we just end up getting a 0 in the left hand side times these non-zero quantities. So this and this, that's it. So it is 0 equal to 1 upon r times del r of r times del u theta by del r, okay, minus u theta by r squared, okay. But I know that my u theta is just a function of r only, okay, which means I can then, replace the partial derivatives with complete derivatives, which means it is, or total derivative maybe, ddr of r times du theta by dr minus u theta by r squared, okay. And let's simplify this. So if we just simply use the product rule here, let's see what will we get. So it's going to be 0 equal to d2 theta by dr2 plus 1 upon r du theta by dr minus u theta by r squared, okay. And maybe what I'll do is I'll multiply the entire equation by r squared, and then I'll get r squared times d2 u theta by dr2 plus r times du theta by dr minus u theta is equal to 0. Okay, so oops, sorry. Okay, so that's it. That's so the seemingly much big and nasty, Navier-Stokes equation in theta direction, that's just, gets reduced to this beautiful ODE. And this ODE is, so frequently used in many applications that it has actually got a particular name. This is known as a Euler-Cauchy equation. Okay, so this is actually known as, in the mathematical literature, it is known as an Euler-Cauchy equation. Okay, see, the reason why this ODE is not so, I mean, is not directly integrable is because of the fact that, first of all, you have these derivatives, second derivative, first derivative, and u theta. That is okay. But more importantly, you have, the coefficients which are variable. Typically, you have r square multiplied with d2 theta by dr2. Okay. But the good thing is, if you can calculate the dimension of these quantities has got the same dimension. Okay. For instance, the dimension of r square times d2 u theta by dr2 is going to be the same dimension of u theta, and it is also going to be the same dimension as r times du theta by dr. So sometimes these kind of ODEs, these are also known as equidimensional equations. Okay, and the procedure to solve this problem, is hinges. So basically, the procedure to solve for u theta hinges on the fact that the individual terms in this equidimensional equation or the Euler-Cauchy equations are of the same dimension. So what we'll do is we will consider u theta to be some form of r power k, where k is just any real number basically. Okay, so k is basically an arbitrary number, and we are going to find out what basically is the value of k is. Okay, so what we'll do is we'll assume, so that's how we do. So we'll assume u theta to be of the form r power k. Okay, then what is du theta by dr is? So this comes out to be equal to k times r power k minus 1, and d2 u theta by dr2, this comes out to be equal to k times k minus 1 r power k minus 2. Okay, all right, so that's it. So what we need to do is we just then need to substitute these derivatives into this Euler-Cauchy equation. So if I evaluate the first term, it is r square times d2 u theta by dr2. So this is r square times k into k minus 1 times r power k minus 2, plus the next term is r times d theta by dr. So it is r times k into r power k minus 1, minus the next term is u theta, which is r power k equal to 0. See, now the good thing is I have an r power k minus 2 and an r square. So I'll get So basically from here I will get a k into k minus 1 times r power k. And then from here I have r power k minus 1 times r. Okay, so I'll have an k times r power k. Okay, and then I have an r power k equal to 0. From which what I can do is I can take r power k common. Okay, and then this becomes k into k minus 1 plus k minus 1, okay, is equal to 0. Okay, so now we have two options. One, r power k can be equal to 0 and this can be anything, but that is not possible, right? Because if r power k is 0, I know that then u theta will just be equal to 0, but that is not possible because I know that u theta has non-zero values at the interfaces of the cylinders, which means that r power k can't be equal to 0. Okay, r power k can't be equal to 0. This only means then the only possible solution is that k into k minus 1 plus k minus 1 is equal to 0. From here, if you evaluate the value of k, so let's do it. So it is k square minus k plus k minus 1 equal to 0. And from here, you will get k to be equal to plus and minus of 1. Okay. So that's it. So these are the two value of k that are possible. And so if you take these two value, the solutions, so one solution will be r. So basically one solution would be a times, or let's say a1 times r power k or r power 1, and the next solution will be a2 times r power minus 1, and then the complete solution is going to be the linear combination of these two individual solutions. So the complete solution of u theta as a function of r is going to be some a1 times r power 1 plus a2 by r. Okay, that's it. That's your general solution for u theta. And that's how you actually solve these Euler-Cauchy equation or equidimensional equation. Okay, so maybe I'll name this. So maybe I should name my equation. So, okay, let's see the numbering first. Where did I stop? So this is 3. And then maybe I'll name these equation as 4. Okay, this simplified Euler-Cauchy form as 5. And maybe I'll name this solution as 6. Okay, so that's it. You have precisely derived the general form of u theta. So all we now need to do is use the boundary conditions at r equal to a and r equal to b to get the unknown constants a1 and a2. Okay, or in other words, we need to use the boundary conditions. Okay, so if I use the boundary conditions, so if I use the boundary conditions, I know that my u theta at r equal to b is what? So my u theta as r equal to b is omega 2 times b, and my u theta at r equal to a is equal to omega 1 times a. Okay. Okay, all right. So let's substitute. So maybe we'll call it as 6a, and then what we need to do is we just need to use 6a in 6. So if I use the first part, the first one, I basically get omega 2 times b is equal to what? a1 times b plus a2 by b. Okay, and then if I use the second one, which is basically this, I get omega 1 times a equal to a1 times a plus a2 by a. Okay, so that's it. Two equations, two unknowns, a1 and a2. That's easily solvable, right? So maybe what you can do is you can multiply this equation by b. You can maybe multiply this equation by a and this equation by b, and then subtract. You'll basically get a2. And then if you substitute a2 in one of the equation, you will basically get a1. I hope that you can do it at your end, and I don't feel the need to basically show you how to solve linear equations and get the unknowns, at least at this point of time. Okay, so do this at your end. It's just two equations, two unknown. That's it. That's all that you need to do. I gave you at least I gave you the idea how to do it. Okay, so I'll just write down the final forms of the unknowns a1 and a2. So you will see that your a1, so your a1 will come out to be equal to omega 1 minus b square by b square minus a square times omega 1 minus omega 2. This is what your A1 is going to be, and A2 is going to be equal to A square B square times omega 1 minus omega 2 by B square minus A square. Okay, I would encourage you to do this substitution, I mean, to solve this equation and check it out that these are the values of A1 and A2. Okay, so that's it. Then we just need to, write down u theta in terms of A1, A2. So maybe I'll call this as 6b. So therefore, your u theta as a function of r is what? It is A1 times r plus A2 by r. So this basically becomes omega 1 minus b squared by b squared minus a square times omega 1 minus omega 2. Okay, this is multiplied with r plus it is A2 by r. So this becomes a squared b squared omega 1 minus omega 2 by r times b square minus a square. That's it. That's your u theta velocity profile. And you can very easily verify that this u theta velocity profile essentially, satisfies the boundary conditions that we just now wrote, some time back. Okay, that's it. That's your u theta velocity profile. Okay. All right, we are not done yet because we also need to evaluate one more velocity profile, which is the UZ, because remember there is also an axial pressure gradient which is actually needed to move the fluid out of the die basically. Okay, so the second thing is evaluate, sorry. Okay, so the second thing is evaluate UZ. And I also know that UZ is also going to be a function of R. Why? That's typically because from the assumptions. Fully developed, which means that UZ is not a function of Z. Axisymmetric, which means that UZ is not a function of theta. Okay, this means that UZ, the only possible way is that UZ, which can be non-zero, is that it can only have variations in the r direction typically. Okay, so we need to evaluate UZ, and at least the drill, you are much familiar with the drill now. So what we need to do is we just need to use the Navier-Stokes equation in the Z direction basically. Okay, so Navier-Stokes equation in the Z direction. Okay, so let's write it down. So let's see what we get when we write the Navier-Stokes equation in the Z direction. I have, well, so maybe I don't have the Z direction in my notes. Okay. Just 1 second. Maybe I don't have the full equation here in my notes, but I can easily get it from the note. Okay, that's okay. I think I can easily write. So I don't have the full Navier-Stokes equation in the Z direction in my notes, but I can easily write that from the theta equation itself. So you can show that your Navier-Stokes equation in the Z direction after, invoking all the assumptions, for instance, steady, fully developed, axisymmetric, no body force and incompressible fluid, all those assumptions, if you use, you will simply see that it just boils down to 0 times 1 upon r dp dz, because I know that the pressure gradient is just going to be applied in the z direction, plus mu times 1 by r ddr of r times duz by dr. Okay, I think this is something that you are going to get, and I think the rest of the terms are just going to be equal to 0. Yeah, so that's it. That's the term that you are going to get. So this is what your z direction equation is going to look like. And please check this out. I actually don't have my complete z direction equation in my notes, and it's very difficult to remember the full equation in z direction. But I believe you can now easily solve this, because this is just you know that the solution to this is just going to be this parabolic profile, right? So uz is just going to be equal to 1 upon 4 mu dp dz times r square minus r. Yeah, so it is going to be what? So it is going to be, of course, you need to, so maybe what you can do is you can do this. So basically what you can do is you can solve this, okay? Solve this and use the fact that your uz at r equal to a is 0 and your uz at r equal to b is 0. So this is something that you can use, okay? And then just try to solve for uz as a function of r. I think that's all that you require to do, okay? I'm extremely sorry I don't have the full equation in my notes, but to the best of my knowledge, this is what the equation look like. You can easily integrate this equation to get the, you know that your velocity profile is just going to be parabolic in nature. Okay, so this is something that I'll ask you to do maybe, or I'll solve this anyway. I'll write the equation a priori and I'll solve this in the next class when we meet. Okay, but anyways, this is something that I don't that I believe you can easily do it. That is a z direction equation. That's simple. But there is something else which I actually want to discuss. But before that, which is actually a special case of this solution. This is something that I actually wanted to discuss today. And but before that, if you have any questions, you can let me know. Okay, and and we will and I'll be happy to clarify if there are any doubts. Okay, maybe I'll stop here for a couple of minutes and then look into certain special cases of this equation. Maybe I'll name this equation. So this is, let's say, 7. Okay, in the meantime, I'll be back in 2 minutes. I'll just fill my mug with some water. Mm. Okay, sorry for the interruption. So, as I was telling, let's look into certain special cases of equation 7. Okay. Again, I say, so please work out the, so just look into any standard book. I believe you can look into the prescribed book for your course and see the z direction. I mean, the equation which govern uz, that is the Navier-Stokes equation in the z direction. Write down the entire equation, invoke the assumption, and you should end up eventually getting this equation. Use the two boundary condition to get uz as a function of r. Okay, please try to do it. If not, I'll show you in the next class. Okay. All right. So as I was telling, let's look into a special case. Okay, which I will say that So in this case, so that's a special case where I'll say that my dpdz is equal to 0, okay, which means that now there is no applied pressure gradient in the axial direction, and this will mean that there is no actuating force in the z direction, which will then imply that my uz is also going to be equal to 0, just like u theta. Okay, and then I also say that my inner cylinder is absent, which means that I can consider a to be equal to 0, and I say that my omega 1 is 0, because if there is no inner cylinder, you can't have a rotation omega 1. Okay, so if I use this information, I hope you are clear. So the first one is that I am saying that there is no applied pressure gradient, which means that now there is no actuating mechanism in the z direction which can drive the flow, which equivalently means that my z direction velocity is going to be equal to 0, just like the theta direction velocity. I'm sorry, just like the r direction velocity. This is wrong. This is the r direction velocity. And then I say that I am just considering one cylinder, which is the outer cylinder, which is rotating with omega 2, and and I say that there is no inner cylinder. Typically, this just boils down to the fact that there is no inner cylinder present. Okay, and this means that no applied pressure gradient. Okay. Okay, so in these circumstances, if you calculate what is u theta as a function of r, okay, just by using these fact into this equation, for instance, you are not going to have omega 1, this is going to be equal to 0, this is going to be equal to 0, and you know that you don't have an inner cylinder, so this a is going to be equal to 0. So if we apply that, you will see that your velocity profile just simplifies to omega 1 times r, and since there is only one cylinder which is rotating, I'll, instead of calling it as omega 1, I'll call it as just omega times r. Okay, so this is what your velocity profile would simplify to if you use the fact that there is no inner cylinder uh, that is present, and of course that this implies that the only way the fluid can rotate is by the fact that the outer cylinder is rotating with some angular velocity omega. Okay, so this special case, this is actually known as, this velocity profile that you have got, this is actually known as rigid body motion. Okay, and this rigid body motion, quote unquote, this is known as a quote unquote, this is known as a rigid body motion, and and this rigid body motion is actually a very special kind of motion that we encounter in fluid dynamics. Okay, and I'll actually tell you why this is the scenario. Okay, first of all, in order to understand this further, let's write the Navier-Stokes equation for this scenario. So ns means the Navier-Stokes equation for this special case. Of course, so I am writing the Navier-Stokes equation considering this special case where there is only one cylinder that is rotating with omega, and of course there is no pressure gradient, so you don't have you don't have the velocity profile in the z direction as well. Okay, and then let's write the Navier-Stokes equation in the r direction. And luckily, I have written the full Navier-Stokes equation in the r direction in my notes. So let's write it down. So this is going to be rho times del ur by del t plus ur times del ur by del r plus u theta by r times del ur by del theta, okay, plus uz times del ur by del z minus u theta squared by r, and this is equal to minus of dp dr plus mu times 1 by, or maybe this is del r of 1 by r times del r of r ur. Okay, okay, plus 1 upon r squared del 2 ur by del theta squared minus 2 by r squared del u r. Okay, so this is del u theta by del theta plus del 2 u r by del z squared. Okay, so I think that's it. Yeah. Okay, so that's the full, Navier-Stokes equation in the r direction. So let's invoke the assumptions. Remember, we don't actually have an r direction velocity because the cylinder's rotation is imparting a velocity in the theta direction only, which means that all the ur components will just go to 0. These things are just going to be equal to 0. This thing is going to be non-zero, and this is very important. We will see very shortly. This pressure gradient is also going to be non-zero because we don't know what is the pressure gradient in the r direction. Okay, that we don't know. We don't know the pressure field in the r direction. That's not given to us. But all we know is that urs are going to be equal to 0. This is going to be equal to 0. This is axisymmetric typically, and this is going to be equal to 0, which means that if I just write down the simplified form, I just have rho times u theta squared by r is equal to del p by del r. Okay, and if I substitute the form of u theta, because I know that u theta is equal to omega r, which means this just becomes rho times omega squared r squared by r is equal to del p by del r, or in other words, the pressure gradient, which is actually unknown, this simply come out to be equal to rho times r omega squared. Okay, can you encounter, or can you tell me what is actually this typical, I mean, more importantly in the right hand side, can you identify this term rho r omega, oops, so can you identify this term rho r omega square? Okay, if you pay a closer look, this is nothing but m, which is the mass of the fluid, r omega squared divided by the volume. Okay, or in other words, this is nothing but the centripetal force per unit volume. That's what you are doing, right? I mean, that's what exactly we get, right? So what I'm saying is that this is important and you need to understand. So if you are considering the motion of a cylinder that is rotating a fluid and you apply the Navier-Stokes equation in the r direction, you can say that even though you don't have a velocity field in the r direction, typically because of the fact that it is no penetrate, I mean, using the fact that fluid cannot penetrate the surface, so you don't have an ur, but still there will be a pressure gradient that will get developed in order to encounter, or in order to, in order to balance the centripetal force. Basically that's what you can interpret from this result. Okay, so this is the pressure gradient, this del p del r. See, we didn't, so if you understand, we didn't actually have a pressure gradient that is imposed in the r direction. Okay, this is the pressure gradient that got developed when the fluid was rotating in the u theta direction with some velocity omega times r. So this is the, so this del p del r is kind of like an induced pressure gradient, that basically gets developed in order to balance the centripetal force, which tries to move the fluid far away from the center typically. So in order to, in order to circumvent that, or in order to balance that, to be more precise, this pressure gradient actually gets developed and we call it as the induced pressure gradient. Okay, and this pressure gradient is actually, the direction of this pressure gradient is actually along the r direction, as you can see from this equation. Okay, so schematically what does it mean is, if I draw, let's say if I draw the scenario here, this is the cylinder that is rotating with some velocity omega, and because of which the fluid will also rotate. And if I draw the streamlines, the streamlines will be something like this, and this is obvious because the streamlines will also be concentric circles. This is obvious because we are only having a non-zero u theta component of velocity. Okay, this is what the streamlines are going to be. Okay, and at any point, if I draw the tangent, this will give me the direction of u theta, and I know that this is basically equal to omega times r. Okay, so this is what the streamlines would look like at any point. This is what the direction of the velocity field would look like. Okay, and what I'm trying to say is, at any radial location, let's say r. Okay, if I draw a fluid element, let's say this basically is my fluid element. Okay, if I draw this particular fluid element, what I can say that maybe I now kind of zoom in this fluid element. This will look maybe something like this. Okay, so I'm kind of like zooming in this fluid element. Okay, so what it says is that, and of course this is my r direction. So what this means is that if you pay closer look, this rho, this is greater than 0, r is always greater than 0, omega squared is going to be greater than 0, which means the sign of, so this del p del r, this is always positive, which means that my pressure at this particular radial location, let's say, so if the thickness of this fluid element is some, let's say, delta r, then my pressure here at p equal to r plus maybe what, delta r by 2, this is actually greater than my pressure at p equal to r minus delta r by 2. Okay, which means at this phase of this fluid element, I actually have a higher pressure and then at this phase of the fluid element. Okay, which means the net pressure force will actually act in this particular direction. Okay, and this actually develop it, so this pressure force actually gets induced because there is an inherent centripetal force that will try to move the fluid element out, away from the center line. Okay, so this is F cent and this is F due to the induced pressure. And at steady state, these two pressure forces get balanced, and this is something that we get from this is something that we get when we apply the R momentum equation. When we apply the when we calculate for del P del R from the R momentum equation using the Navier-Stokes equation, or just the R momentum equation. Okay, so this is the number. This is the first thing that I want to convey. The second thing is that the reason why this is known as a rigid body motion is that you can show that this fluid element does not deform. This fluid element typically does not deform. Okay, the reason from this, so if you calculate something which is known as the viscous stress, this is something that you know, and if you calculate the r theta component of the viscous stress, you can show that. So if you calculate the r theta component, you can show that your tau r theta essentially come out as del r of u theta by r plus 1 by r del ur by del theta. And I know that my ur is 0. I don't have a motion of the fluid in the r direction. But I know that my u theta is just omega r, which means u theta by r is just equal to omega. And I just substitute it here. Okay, which means that I have tau r theta is equal to r times del r of just omega. Now, I know that omega, which is the rotational velocity of the cylinder, this is just a constant, right? And because this omega is just the rotational velocity of the cylinder, and this is just a constant, which then means that this quantity del r of omega, this is just going to be equal to 0 because omega is just a constant, it's just the rotational velocity of the cylinder. Okay, which then means that my tau r theta, and I know that this is equivalently equal to tau theta r because stress is symmetric, this is just going to be equal to 0. Okay, so because tau r theta is going to be equal to 0, there is no way which can actually deform the fluid element in this or in this particular direction. That is, when this fluid element undergoes rigid body rotation along this axis, maybe, okay, its shape is just going to be, its shape is just going to remain the same. That is, the shape of the fluid element at this position A is going to be exactly same at this position B. That is, the fluid element will not deform, and this is also going to be same at the position C, which is this, which is basically maybe this, and at all other positions wherever we want to draw it. Okay, that is, when the fluid undergoes motion in the u theta direction, the fluid, if you pick a fluid element, okay, the fluid element will not deform, or in other words, we don't have a viscous stress component r theta in that particular direction. Okay, that's the typical reason why this motion is known as a rigid body motion. And this is a very few cases where you can say that your fluid is kind of actually behaving like a solid because it is not undergoing any deformation, right? Because we all know that if a fluid flows, usually it deforms because of the viscous stresses. But this is that particular, it's a very rare and that particular scenario where you can say that the fluid is just undergoing a rigid body rotation about a particular axis, which is basically the z axis in this scenario. Okay, so that's the reason why this particular scenario is known as a rigid body rotation. Okay, so in other words, from here you can say that the fluid element never deforms in the course of its motion. Okay, and that's typically the reason why we call this type of motion as rigid body motion. So two things, the two t so the in summary, there are two takeaway things in this special case, which is that when we don't have an inner cylinder and we don't impose any pressure gradient in the z axis, what we see is that number one, in the r direction, although there is no velocity or an active velocity field ur, there is an induced pressure gradient that gets developed in order to in order to tackle the centripetal force which is trying to move the fluid outward. Basically, it basically balances the centripetal force. Okay, such that the fluid continues to circle around in its orbit. That's the number one thing. The second thing is that during the course of motion in its orbit, okay, the fluid element doesn't undergo any deformation, typically or simply because the viscous stress tau r theta component, which is actually responsible for this deformation, comes out to be equal to 0. Okay, that's the reason why at each and every point in its journey, the shape of the fluid element remains intact in its circular orbits. And that's a special case where you can actually say that your fluid is behaving like a solid and it is just moving or it is just rotating with a fixed angular velocity about its axis, which is the z axis in this scenario. Okay, so these are the two key takeaway things that I wish to convey through this special example of this problem. Okay, uh, but the overall problem that we solved, I'm extremely sorry I couldn't show you the z component of the velocity profile because I didn't have this, so I cannot remember the entire z component of the velocity, or I cannot remember the entire Navier-Stokes equation in the z direction, right? So I didn't write it in my notes. So that's the reason why I didn't have. Anyways, I just gave you the idea how it will look like. Please verify this at your end and invoking all the assumptions, and if not, I will try to solve it in the next class before starting the contents of the next class. Okay, sorry for that, but apart from that, we solved the entire problem where we had rotation of the cylinders and a motion of the fluid in the z axis, and then looked into these particular scenarios. And before that, we looked into how the motion in curvilinear coordinates takes place. Typically, we discuss cylindrical coordinate here, but later on, if in a space in a chapter known as creeping flows, we will also see a glimpse of something known as the spherical coordinate and how to solve equations in spherical coordinate. Okay, we will basically looked at aspect as well. But this is something that I wish to discuss today. Uh, Please let me know if there are any questions. And in the next class, we'll look into something which is known as the scaling analysis of the equations. And we looked into like how do we non-dimensionalize equations and something known as the characteristic scales. And then we'll proceed with the discussions of, the further discussions of that week, basically. That is, I think that would be week 4. And then there is something that we'll see. Okay, so please let me know if there are any questions. And I'll also request you to please actively participate in the discussion forum of the course had you arise, or if at any point where you are actually trying to solve the assignments or watching the lecture series, if there are any doubts, please post it in the discussion forum such that we can address the doubt you know, then and there itself. And also, if you have any doubts pertaining to these discussion hours, you can also post in the discussion forum as well. All right, if no questions, then we will call it a day, and we will meet in the next week again in the same at the same time using the same link as you know, and take it up from here onwards. Okay. All right. Thank you very much for watching these videos. See you next week.